All right, class, it is 10, no, it's what, 9:45. I'm getting ready to start. We just completed the ABG exam. I'm very pleased with this exam. Very pleased. I'm pretty sure some of you were very surprised with the way you were feeling, but did so much better than you thought you would do, and some might not have done as well as they thought they would have. And we're going to go over that now, okay? I'm going to go over the test right quick, but I won't record. I cannot record while I pull up the test because we do have students who have not completed the test, as well as this will be a recording for out there for future students. Okay, so I'm going to pause recording while I share my screen and go through the exam. All right, if you are live, you will be able to see it. If you're not, you won't. Okay, all right. Share my screen. I'm pretty sure you'll find that something that you did that you should have not done for that. All right. Here we go. All right. Can y'all see the test? All right. Let me stop the recording. All right, guys, we just went over the live exam that we just took. Now we're going on into the next lesson, which is gas physics. Gas physics. We're going to be talking about tanks and cylinders. Well, cylinders. They don't like to call them tanks, but they're oxygen cylinders, other kind of gaseous cylinders. We're going to talk about, hold on. We're going to talk about other gases. We're also going to get back into that when we talked about the gases of the atmosphere and how they exert their own pressure. I've already taught you that, but we're going to learn that. That's what's learned in this lesson, okay? So that's going to be cool because you already have had a touch of it and you already understand that part, okay? But these are going to talk about different theories and laws that have been put into place that have to do with gas. For example, what happens when you release the volume out of one of those spray cans that spray your computer, that spray your keyboard off? Get a little can with a little stick and you spray it and it sprays your keyboard real good, real high pressure comes off, right? The volume of it is releasing, it's going down real fast. What happens to the feel of the can in your hand? It gets cold. So as volume decreases, so does that temperature, okay? That will be somebody's law, all right? Somebody found out that happens all the time. When I have an oxygen cylinder and I turn it on real fast, it's going to get almost frozen on the end because gas is releasing. The pressure is going down as well as the volume is going down. As they go down, the temperature also goes down, okay? Or if you put what if you put a aerosol can, like a Lysol can, and stick it right on top of a stove? What's going to happen? It's going to explode because the heat has increased and so will the pressure inside the can. That's another law, okay? So those are the kind of laws that you're going to learn about. I'm gonna play a video of the gas laws, probably not today, but it might be. And I have to be careful because if I'm recording the video, then it's going to might block my presentation from you, right? So when I do show the video, I'm going to have to pause the recording. You'll have to watch the video on your own because the video is in the module, okay? The gas laws video, you just watch it, okay? But it's kind of like a little cartoon about a couple of different guys and their laws, all right? So let's go on and get into it. Let's open up gas physics. If you didn't do well as you thought you was going to do on this test, don't let it bring you down, okay? It's okay. You're not going to get hundreds on every one of them. Happens, all right? Just figure out what you did wrong, do the little practice and review, and solidify that, okay? That's not a big deal. All right. So let me share my screen to the lesson plan. All right, here we go. Make it a little bit bigger. Make it a little bit bigger for Ms. Rose. All right, so students will be able to discuss and demonstrate the gas laws and physics in use in the field of respiratory care. Be able to describe Avogadro's law. So these are the laws. I recommend that you make some note cards for these laws, or you put them on a separate sheet of paper in your notes when you kind of have, like you have a page for formulas, you have a page for laws, okay? That way, if you hear any more laws as you go on in your career, because the notes you're taking now, I would hope that you keep them to 220. Just put another section in there. Get you a bigger binder, whatever you need. You need to have 210, then you can have 220, because when you start studying for the board and the end test, you're going to use all of this, all right? So don't just say I got through 210, I'm through, and put that up and start me a new binder for 220. Don't do that, all right? You have to know, and you'll be frequently going back to 210 for information, all right? So in your page that you make for laws, or whatever color you use just for laws, sometimes you just use a certain color. I use pink highlighter for my laws, and somebody might say I use blue highlighter for all my formulas, and then you kind of know that, right? So it makes it easier to find when you're studying. So you'll be able to discuss Avogadro's law relating to a mole of oxygen, relate Dalton's law to the partial pressure of oxygen in the atmosphere. When we talked about all of those pressures, all of those percentages in the atmosphere and converted those all into pressures, that's Dalton, okay? That's Dalton's law. So you've already kind of heard about his law. I said it's kind of like the barometric gumbo, right? All of the different ingredients in the gumbo come together to make one taste, right? The pressures in the atmosphere come together to make one pressure, which is 760. But if I pull the carrots out of the gumbo alone, the carrots has its own flavor. It's just like if I pull one of the gases out of the atmosphere, it exerts its own pressure. And so Dalton says that the total pressure is a sum of all the individual pressures. That's Dalton, period, okay? Recall the concentration of oxygen in the atmosphere. You already know that's 21%. Be able to apply the alveolar equation. So we're going to be back into that again. So you already got that, right? Relate ideal gas laws to situational use. Discuss agencies and regulations of gas administration, the DOT and the FDA and all the different organizations that have their hand in how oxygen cylinders or medical gas cylinders are formed, tested, transported. All of those have a hand. Somebody got a hand in that, right? Safe storage, all that kind of stuff. Because a hospital or the school can be dinged if the oxygen tanks are not stored properly. Very, very dangerous, okay? Recall the color codes. Mandatory for E-cylinders. We have a lot of safety factors or safety systems for oxygen and other gases, because you don't want to put an oxygen regulator on a nitrous oxide tank and say, here, this is oxygen, right? Or a poisonous gas, right? You can kill them. And so there are some safety mechanisms we use to determine different cylinders, right? One of the safety mechanisms is color coding, all right? Oxygen is green. Oxygen cylinders are green in the United States. Everywhere else in the world, they're white, okay? Everywhere else in the world. But that's just one of the safety systems. Demonstrate regulation of cylinder markings. There's certain things that's written on the cylinder on the front, some on the back. Calculate how long it lasts, the duration of flow, right? How long, if I say Mr. Johnson is on an E cylinder at 2 liters per minute, how long would it last? You have to be able to calculate that formula and tell me he has 2 hours, he has 3 hours, he might have 30 minutes, okay? Does he have enough time to go to the dog track before he go home, or do he need to get another tank? All right, because when you go to the casino, you see people walking around with oxygen, okay? And if they run out, they show it, okay? So they have to know how long they have, all right? Discuss cylinder testing, how often it's tested. Recall the difference between liquid and oxygen, gaseous oxygen. There is a difference. Oxygen it starts as a liquid, very, very cold liquid. And as it raises to a certain temperature, it turns into gas, okay? So when they deliver oxygen to the hospitals, it's liquid. A big liquid tank will hook up to it and fill it with liquid. It'll be frost all over the connection, look like snow, because it's very, very cold, huh? Like freezing cold, yeah. Next Air and all those folks, that they would deliver that liquid to the hospital, into the big, huge liquid tanks that are kept at a certain temperature. And then as the liquid passes through coils, it gets warmer and turns into gas. And that gas is pumped into the walls of the hospital, okay? Because you can go much farther with liquid than you can with gas. So that's why we get it to the hospital as a liquid, right? Because it lasts much longer and we can do much more with it, okay? If we would have got it as a gas, it'd be filling up two or three times a day, okay? All right. Differentiate, how you say that word? Differentiate between single stage, multi-stage, preset, and adjustable flow meters. Now we're getting into the, how do we deliver the oxygen that we just talked about to the body? How do we get it? Do we just put our mouth on the cylinder? No. There's regulators that we put on that bring that pressure down, because that will blow your mouth open, okay? And so there's regulators that bring the pressure down to a certain working pressure of about 50 psi. And some of them get to it in one stage. Some of them have to do 2 or 3 stages, right? Multi-stages to get to it. Some of them are preset, and some of them are adjustable. Flow meters. You're going to learn the different types of flow meters. Uncompensated and compensated flow meters, which is easy to understand. There's no more thinking like, hey, this is an easy set right here. So if you didn't do well on this last test, this ought to be a real easy A on this. You just don't take it for granted now. But if you study this one like you studied the last one, it should be a breeze, okay? And then make adjustments to using the oxygen tank. There's going to be a lab with this one, right? You do have a lab. We're going to learn. There's going to be some something in the lab book that you're going to have to do in order to check off in your lab. I have a video already in the module that you can watch. You can watch it tonight if you want to. But go ahead and get familiar, seeing me hook up the different regulators and turning on the tank, the steps to turn it on, the steps to turn it off, things like that, because that's what you'll be doing yourself in the lab, okay? And then describe the function and advantages, disadvantages of the Bourdon gauge, okay? All right. States of matter. So let me see. I think I have a PowerPoint for this one. Might look a little bit better. No, I do. to do it like this because I know it's one in the module. So let me go to the module and pull up the gas physics PowerPoint. All right. Gas physics. Do y'all see a PowerPoint on your screen? Okay. Gas laws and physics. I'll cut the light off. All right. States of matter. We have 3 states of matter. Of course, we have solid, liquid, and what? Gas. Same matter, just in 3 different states. All right. Gases. Molecules. What are gases? There are molecules that are continuously moving, right? Gases are molecules that are continuously moving. And we're going to talk about Avogadro's law. He's going to talk about his law states that 1 gram of atomic weight of any substance contains 6.02 times 10 to the 23 atoms. This is known as 1 mole. Okay? 1 mole is 6.02 times 10 to the 23 atoms. He says 1 gram contains that many atoms. Okay? 1 gram of any substance, right, contains this kind of this many atoms. This is known as 1 mole, all right? And 1 mole of a gas at standard temperature pressure, that's what STP means. 1 mole of gas at standard temperature pressure occupies about 22.4 liters of space. Okay, 1 mole of gas is about 22.4 liters of space. Okay, so how many moles, knowing that 1 mole of gas is 22.4 liters, then let me see before I ask that question. So I was going to ask, how many moles would you have at tidal volume? Your tidal volume is about how many moles? If 1 mole is 22.4 liters, then what is the normal tidal volume? Normal tidal volume is 500 milliliters or 0.5 liters, right? And so you'd have to do 0.5 divided by 22.4, and it's about 0.022, right? 0.022 liters. So that's letting you know how small that is, okay? But 1 mole of gas occupies 22.4 liters of space, okay? 22.4. So I always say, when we talk about Avogadro, I'll call him Avogadro the mole. I have a little pet named Avogadro the mole. All right, sitting in his little hamster cage, right? Avogadro the mole. If you think about that, you'll never forget that his law states talk about the mole. Okay. Now, barometric pressure, PB. We already said what that was. PB is barometric pressure, and the normal barometric pressure is 760 millimeters of mercury. Now, it's also considered 14.7 psi, or 1,034 centimeters of water, or 33 feet of water. Okay, So normal barometric pressure is all four of those. We mostly talk about the millimeters of mercury, right? But you might get a multiple question that says the barometric pressure is what's true about the barometric pressure, right? And some of these might be on there. Make sure you add them to your list. Normal is 760, but it's also considered 14.7 psi at 14.7 pressure per square inch is also called barometric pressure. 1,034 centimeters of water is also known as barometric pressure, right? And 33 feet of water can be barometric pressure. The reason why they talk about that is because, especially the feet of water, because when you go deeper and deeper into water, you're going down more atmospheres, right? You're going down and everything gets heavier and heavier the deeper you go in the ocean, right? If you're going in the ocean, you're going deeper, deeper, deeper. That is going down more atmospheres, because barometric pressure is considered to be one atmosphere, right? One atmosphere, which is barometric pressure, is 760 millimeters of mercury. So 2 atmospheres will be how much millimeters of mercury? 760 times 2, 1520. 1520, right? So 2 atmospheres will be 1,520 millimeters of mercury, right? And then 3 atmospheres will be 760 times 3. And so they're trying to show you how does that correlate with depth. So at 33 feet of water, you're feeling about barometric pressure. 2 atmospheres will be 66 feet of water, right? And then 3 atmospheres, of course, will be 99 atmospheres of water, okay? I mean, atmospheres of water. 99 atmospheres. All right, 3 atmospheres would be 99 feet of water, I'm sorry. All right, but you mostly have to do the 760. I'm not gonna try to make you memorize all those, just know them though, because you might have a multiple that throws one of them in there. All right, I want you to say, if it gives you 1,034 centimeters of water, but no, that ain't it. You know, that is part of it. So make sure you know that. All right, now, we talked about the water vapor. When we inhale gas, the nose, which is the primary humidifier of the body, heats and moisturizes the air we breathe, right? It gives us the humidity that we need. And that humidity is known as water vapor. Water vapor, AKA humidity. Water vapor, AKA humidity. And that water vapor exerts a pressure, right? And we said the partial pressure of water at 100% relative humidity and 37 degrees Celsius, which is normal body temperature, right? That's all they're saying. Is how much? Pressure of water is what? 47 millimeters of mercury. 47 millimeters of mercury. That is the normal pressure of water inside the alveoli, inside the lungs, okay? Water vapor pushes its own pressure. So you take that into consideration when you're doing these formulas, okay? And finally, Dalton's law. Here's another law. We just talked about Avogadro. Now we're talking about Dalton. Dalton says the sum of the total of the individual partial pressures of gases in the atmosphere are equal to the barometric pressure. That's what I said, the barometric atmospheric gumbo, right? Atmospheric gumbo, or barometric gumbo, okay? Every little pressure or every little gas there exerts its own punch. The carrots have their own punch, the shrimp has its own punch, the rice has its own punch, the sausage has its own punch, right? And they have their own separate punch, but when you put them all together, they make one punch. Whoever made it, right? Susie's gumbo has a taste, right? But each one of them have an individual taste if I take them out. So that's all he's saying. If I put them all together, they equal one taste or one pressure, right? In order to find that, it says barometric pressure is the pressure of nitrogen plus the pressure of oxygen plus the pressure of trace gases. That's all he's saying. Because how much pressure did we say nitrogen was? Do you remember? Well, not pressure, but percent. How much percent of nitrogen is in room air?
71.
78. Yeah, 78 is a lot, right? And then oxygen is 21%, right? And then carbon dioxide is like 0.03%. and trace gases is 0.01%, right? Argon was like 7% or something like that. I don't remember, but it's gonna be on here. So they don't even really count the trace gases or the argon. Barometric pressure just kind of throws those in with trace gases. You know, the trace gases and the argon is kind of thrown in together on this formula here. But in order to find out what the pressure is of a certain gas, remember we just multiplied by barometric pressure, right? So for instance, to find the pressure of nitrogen in the air, you simply do barometric pressure times the percent of nitrogen. And percent of nitrogen was 78%. And when we have to do 0.78, right? Turn it into a decimal. So 760 times 0.78 gave us a pressure of nitrogen of 500 and something, right? Let's see. 0.78 times 760, 592 or 593, right? About 593 millimeters of mercury is the pressure of N2, which is nitrogen. Okay, remember that? All right, what about the pressure of oxygen? Tell me what the pressure of oxygen is. The pressure, I know the percentage is 21%, but what's the pressure? How much pressure does that exert? Using that bottom formula right there. So that'll be pressure of O2 equals barometric pressure times percent of that oxygen. Huh? 159. 159 millimeters of mercury. That's how much pressure that oxygen exerts in the atmosphere. It's 21% of the atmosphere, but it kicks at 159 millimeters of mercury. All right, and nitrogen kicks at 593 millimeters of mercury, right? So nitrogen is way more than oxygen is. All right, and you can do the same thing for the rest of them. All right, so here go those concentrations. Oxygen is 20.95, so we call that 21%. Okay, percentage of oxygen rounds about 21%. Nitrogen is 78%. Argon is 0.93%. I don't know why I was thinking it was 7, but it's 0.93%. And carbon dioxide, 0.03%. And trace gases, 0.01%. Those are all of the gases in the atmosphere. Each one of those exerts its own pressure. So you said that oxygen was 159. You said that nitrogen was 593. Well, what is argon? How much pressure does argon exert? Seven what? No. You got to change that 0.93 to a smaller decimal. Remember, you always got to move it 2 places to the left to turn it into a decimal. It's still in percentage. So 2 more places. So 1, 2. So argon, yeah. So argon is 0.93, but you gotta make it more of a decimal to change from percent, because it's 0.93%. I need to know what that is. It's just a decimal. There you go. So it will be 0.0093 times 760. So you gotta move that decimal 2 places to the left. Don't forget that. Anytime you go from a percent to a decimal, you must move the decimal 2 places to the left, no matter what the number is. Okay, so that would move it from here. So look right here, it's right here now, so I have to go 1, 2, so I put another 0 right there. So now it's 0.0093 times 760, which gives us 7.08 or something like that percent. That's why I was getting that 7 from. 7.06 millimeters of mercury. Okay, and then what about carbon dioxide? How much does it exert? Got to do the same thing with that one. .228. 0.228. Okay, 0.228. And this is why, guys. This is why. This is why the carbon dioxide from the capillary flows into the alveoli, right? Because inside the alveoli, it's only 0.228. When you breathe it in, it's only 0.228 in the atmosphere, right? The pressure of carbon dioxide is 0.228. That's small. But the pressure of carbon dioxide in the and the capillary is about 40 millimeters of mercury. And it goes from high to low, right? Gas has to go from high to low. So once that 40 reaches up against that alveoli, that's only 0.228, that 40 will go into the alveoli so that you can exhale it, okay? And the oxygen inside the alveoli is about 100. Now, the reason why it's not 159 is because we have to subtract the water pressure and the carbon dioxide from that number, okay? And that gives us a P big AO2 of about 100. But in the capillary, it's only about 40 millimeters of mercury in the vein, right? The venous blood. And so since it's 100 in the alveoli and 40 in the capillary, it's going to go into the capillary because of the pressure gradient, all right? High pressure to low. That's how gas moves because of difference in pressure, all right? So you see how we use these things from what we've already learned to build it on. We're building a foundation, all right? Just a picture of the atmosphere here. All right, application of Dalton's law to the lung. Now, this is getting ready to show you the breakdown of the alveolar air equation. Thank God we've already learned the alveolar air equation, but this is a breakdown, okay? So this is just helping you understand it a little bit better. A, partial pressure of gas equals P bar times the concentration, right? So we already learned that. 760 times 0.21 is 159 millimeters of mercury for oxygen, okay? Now, in the lung, water vapor also exerts a pressure of 47 millimeters of mercury. Thus, it changes the pressure of the atmospheric gas in the alveoli, all right? So we have to get rid of that water pressure, right? So we have to say barometric pressure minus the water pressure, which leaves us with 713, okay? That's how we get to 713, right? That's the first part of the equation, all right? Understand? Okay. Now, because of that change in pressure in the alveoli, the partial pressure of O2 is also changes. So now, PO2 is 713 times 0.21, right? Because, listen up, at first to find the pressure of oxygen in the atmosphere, we had to say 760 times 0.21, right? But now we have to say, we took out the water pressure from that, and that left us with 713. So now to find the pressure of oxygen in the alveoli, we have to say 713 times 0.21, right? And that gives us 149. Well, then we take that 149 and subtract that CO2 from that, because CO2, whatever that P little CO2 is, we take that, remember, we subtract that number, CO2 over the RQ, we got to subtract that from it, and that's what leaves us about 100, right? That's what gives us down to about 100. But let's keep watching. All right, so we have taken in a good deep breath of air, right? And outside, the pressure of oxygen is 159 outside, right? But when it got in the lungs, we have to say now we have to take out the water pressure. So that barometric pressure minus the water pressure is 713. So now we take 0.21, which is the amount of oxygen we just pulled in from the atmosphere, times 713, and that gives us 149 millimeters of mercury, okay? Now, look at D. It says in the lungs, the CO2 is higher than in the atmosphere and affected by the respiratory quotient, which is the unequal exchange for O2 for CO2, okay? Respiratory quotient is burning, using up our O2 and producing CO2. That's respiratory quotient, excuse me. So thus we have to take that 149 millimeters of mercury and subtract the PaCO2. The normal PaCO2 is 40, right? Perfect, 40. All right, so just keep that in mind. So CO2, the normal CO2 in your blood, because 35 to 45, 40 is right down the middle, okay? That will be the normal range. The normal absolute. If they didn't tell you what the CO2 is, you use 40 because that's the normal, okay? So you take the 149 minus the PaCO2, right? And then you got to divide it by the respiratory quotient, which is 0.8. So an example, 149 minus 50 gives us 99 because 149 minus a CO2 of 40 divided by 0.8. So what is 40 divided by 0.8? 50, see? So 149 minus CO2 divided by 0.8. If a regular CO2 is 40 divided by 0.8 for a regular respiratory quotient, that gives me 50. So now I have 149 minus 50, and that gives me what? 99. So PaO2 is about 99 millimeters of mercury. P big A O2 leaves us with about 99 millimeters of mercury. Thus, that is the partial pressure of oxygen in the alveoli. So you see the journey that the oxygen has to take, right? There's a mathematical journey that has to be done, okay? So before I go on to the next slide, we got the partial pressure of oxygen in the air is 159 if you do by atmospheric pressure. But we can't do that in the lungs because we have to take account the water vapor pressure, which is 47. So we take the 760 and subtract the water pressure away. That leaves us with 713. Now we can multiply the 713 by the oxygen that we just breathed in, which was 0.21. So 0.21 times that 713 gives us 149, right? Now let's look at the other side of the equation. The other side says carbon dioxide divided by the respiratory quotient. A normal carbon dioxide is 40 divided by a normal respiratory quotient of 0.8 leaves us 50 on that side. So now we have 149 minus 50 gives us a alveolar air tension of 99 millimeters of mercury, okay? That's the process into finding out how much oxygen pressure is in the alveoli, all right? And that changes with a difference in temperature. It can change with a difference in CO2, right? It can change at a different barometric pressure, right? Because what if it's not 730? What if they tell you to use 700 barometric pressure? Then you have to do 700 minus 47 and then multiply by the oxygen, okay? So things can change. Your respiratory quotient could be 1.2, right? Whatever going on in the body, depending on your diet, right? How much carbs are you taking in? Things like that. All affect the amount of oxygen inside your lungs, okay? So this is something we've already learned, but this is breaking it down a little bit better for you. Understand how they got those numbers. All right, so here's the equation in a nutshell. P big AO2 equals FiO2 times the barometric pressure minus the water pressure minus the pressure of carbon dioxide divided by the respiratory quotient. And here are all the lists right here of what they are, okay? Sometimes you'll see this one right here, guys. Sometimes the doctors will leave off the respiratory quotient. Sometimes it's a modified one when it just says P big AO2 equals the P bar minus the water pressure times the FiO2, subtract the CO2 from it, and that's it. They just leave the respiratory quotient off. Sometimes they do that. You'll see it either way, okay? In both ways, though, the CO2 is always considered to be equal to the P big A CO2 because of the rapid equilibration of carbon dioxide, which is 20 times faster than oxygen. So what they're saying is it's always considered to be equal to the P little a CO2 is always considered to be equal to the P big A CO2 because of the rapid equilibration of carbon dioxide, because carbon dioxide diffuses how much faster? 20 times. Carbon dioxide 20 times faster, right? So that's important. It's 20 times faster. I knew it was a little. All right. So this is the quotient here, respiratory quotient. This is the whole equation here for P big AO2. This is breaking down Dalton's law, okay? Dalton's law simply says that the individual gases exert their own pressure, but if you add them together, it equals one big pressure. That's all he's saying. That's all you got to know for Dalton's law to be able to explain it. But this is showing you how we arrive at it in your lungs, okay? How do we arrive at that pressure of oxygen in your lungs through the alveolar air equation. All right, now we're gonna get into some ideal gas law. So let's take a 10-minute break. Let's take a 10-minute break. It is 10:40. Come back at 10:50. We take a break to 10:50. We're gonna get into those gas laws because there's some triangles I gotta draw to help you remember the gas laws, okay? I'm going to put those on the board, all right? So I'm going to stop my recording. All right, so now we're resuming recording. I'm about to pull this camera up on the board where you can see my gas laws. Okay, we're talking about the gas laws. There's 3 major gas laws I want you to know. Boyle's law, Charles's law, and Gay-Lussac's law. Okay, these are 3 that I want you to understand. So I'll put them on the board. So I'm going to share my screen. Well, I'm unsharing my screen and kind of go over them. Then I'll go back and let you write what you need to write. Okay. All right. All right. All right, so 3 laws that I want you to focus on. Boyle's law, Charles' law, and Gay-Lussac's law. Can y'all see that on your screen? Good. Okay. All right, first of all, let's do Boyle's law first. Boyle's law says that, and they all talk about if something is constant. Just bottom line, what you need to know. Boyle's law says that volume and pressure are inversely related. That means if the volume goes down, the pressure will go up. If the volume go up, the pressure would go down. They're inversely related. Boyle's law is also the only one that's inverse. Okay? Boyle's law is the only one that is inverse. The rest of the 2 are directly related. Okay? So that's why I always do Boyle's law first. I meant to draw it first, but whatever. All right, so let's look at Charles's law. Charles's law states that temperature and volume are directly related. So if the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down. If that happens, that's Charles's law, signified as volume 1 over temperature 1 equals volume number 2 over temperature number 2. Okay? Boyle's law says that if volume goes down, then pressure goes up. If pressure goes down, volume goes up. Volume and pressure are inversely related, signified by pressure number 1 times pressure number 2 pressure number 1 times volume number 1 equals pressure number 2 times volume number 2, because you do multiplication in your algebra. They're inversely related. Boyle is inversely. Okay, remember that. If you see inversely, they're talking about Boyle. And finally, Gay-Lussac. Gay-Lussac says that temperature and pressure are directly related. Therefore, if the temperature goes up, the pressure goes up. If the temperature goes down, then the pressure goes down. Okay? That's signified by pressure number 1 over temperature number 1 equals pressure number 2 over temperature number 2. Hello? Hello? All right, that's Gay-Lussac's law. These are the 3 gas laws, okay? The 3 gas laws. So I'm gonna let you get some time to write that down. You need to have your look, they're best signified by triangles. They're in your book, I think, as triangles. So you need to use those as much as possible. Help you understand, okay? Now, when we get back to the notes, I'm going to talk about what's constant, okay? So evidently, talking about temperature and volume on this one. So look at Charles's. Temperature and volume are directly related when pressure and what's left? Temperature, volume, pressure. Okay, yes, that's what I'm saying. Mass, that's what it is, mass are constant. But I said, when I get to the notes, I'll show you what's constant. But what you need to know is that when you're talking about Charles' law, temperature and volume are directly related. They go the same way. Boyle's law says that volume and pressure are indirectly related. They go opposite ways. And Gay-Lussac says that temperature and pressure are directly related. They go the same way. Okay? All right. Now, I'm going to show you a video that will talk about those three laws. And then they also go into kind of figuring out to give you a little sample problem. Say if the balloon is this, and they talk about kilopascals. You don't have to worry about the kilopascals. I just need you to know what we're learning, which is the basics, okay? All right, so let me move this out the way. And do what those concepts first, and then we'll move on. Floor is dirty, and I won't be dripping like that. Yes. You don't want? Good. Oh, my bad. All right, so let's share the PowerPoint. Continue to. Oh. All right, so we'll go back to this last one. Boyle's law. Now, the ideal gas law, don't worry about the ideal gas law. Boyle's law says if temperature and mass are constant, there it is. If temperature and mass is constant, then volume and pressure are inversely proportional. And so that constant one is easy. It's mass and whatever one ain't in your triangle, okay? In Boyle's law, volume and pressure are inversely proportional, right? And so temperature is what's left. So temperature and mass must be constant if they're constant. But they're not going to ask you much about that. Just know that Boyle's law says that when temperature and mass are constant, then volume and pressure are inversely related. Inversely. One go up, the other goes down. Okay? Charles's law says that if pressure and mass are constant, then temperature and volume are directly proportional. Temperature and volume are directly proportional. Now, I told you another student told me that Charles is watching TV. Right? Charles is sitting in the back watching TV. Temperature and volume, if you like that. Okay? And Gay-Lussac says that if volume and mass are constant, then pressure and temperature are directly proportional. Remember, Boyle is the only one that's inversely, okay? The other two are directly proportional, all right? So they said Charles is watching TV, and Gay-Lussac is at the clinic doing physical therapy, PT. If that helps you, it helps you. If not, it don't, okay? I'm just throwing it out there. Thought it was cute. Okay? Good? All right. So make sure you guys write those triangles down on something and memorize that, okay? Who you talking about? When the question says, because it's going to say if volume and mass are constant, then pressure and temperature are directly proportional according to who? You need to say, oh, that's Gay-Lussac, okay? And then it may say if pressure and, I hate this mass. If pressure and mass are constant, then temperature and volume are directly proportional according to who, right? That's Charles's law, okay? All right, now, the triangle demonstrates the relationship, so that's why I did the triangles, all right? Now, when we talk about temperature, all gases are measured in Kelvin. And what did we say? How do we say we get to Kelvin? What is C? Celsius. Celsius plus 273 is Kelvin. All right, so when we are trying to measure the temperature of a gas, it's not in Celsius or Fahrenheit. Gas is always measured in Kelvin, okay? So you must best believe that you're going to have a question that says, well, if I had a gas that was measured in Fahrenheit, what would that be in Kelvin? Okay, then of course you're going to have to go from Fahrenheit to Celsius, and then from Celsius to Kelvin, okay? All right, oxygen cylinders. Oxygen cylinders. These are just some different types. We have several different types of oxygen cylinders, but you see how it's green at the top? That's for oxygen. Green means oxygen. In the United States, what color is it in Europe? White. White. All right, now, here goes the red tape. The bureaucracy when according to cylinders. Everybody has their hand in cylinders, either production, transportation, storage, purity, testing, right? Everybody got something to do with it, right? And so the agencies that regulate the gas administration is the DOT is one of them, the Department of Transportation. You're like, what? Yes, the Department of Transportation. Used to be called the ICC. They regulate the construction, transport, and testing of the cylinders. The Department of Transportation is responsible for the construction, transport, and testing of all gas cylinders. What's wrong? I wonder why I was getting a little stuffy and fan cut off. All right. The next agency will be the HHS, which is the Department of Health and Human Services. They used to be called the HEW. You don't have to worry about all that, right? But they have inside the Health and Human Services lies the FDA, which is the Food and Drug Administration. It is part of the HHS, which is the Health and Human Services Agency. So the Health and Human Service Agency houses the FDA, and they regulate the purity of the gas. Because you say it's oxygen don't mean it's oxygen, right? What if Miss Rose had her own oxygen cylinder company and she's pumping regular air in there and saying it's oxygen, getting paid, right? Nobody would really know that except for it's tested, okay? It has to go through, FDA will come through and test, make sure that you say it's 100% oxygen in that cylinder, that there's 100% oxygen in that cylinder. It's not 60-40. It's not a mixture of oxy and helium. It's not nitrogen and oxygen. It's not room air, period, right? Now, room air, guys, is going to be called medical gas from this point on, okay? When we're talking about room air, you'll still say room air here and there, but when we're talking about cylinders, it's talking about medical gas. Medical gas is room air, just pure room air, okay? It's got a mixture of everything, right? Everything that's in the atmosphere is in that gas, because sometimes you need flow more than you need oxygen, right? What happens if you're riding down the street in the car and the windows are up, right? And you get a little stuffy or you get a little short of breath. What's the first thing you do? You're riding in the car on the highway, whatever, or wherever, and your windows are up and you start feeling short of breath. What's the first thing you're going to do? Let the window down. But what's the percentage of oxygen outside? What's the percentage of oxygen outside? 21%. And what's the percentage of oxygen inside your car? 21%, right? You ain't got no oxygen tank hooked up in your car, do you? That's 21%. So why let the window down? It's the same oxygen, right? So it's difference between oxygen and flow. You guys are going to have to understand that there's a difference between oxygen content and flow. Sometimes your patients need more flow. Right, you giving me oxygen, but hell, I need flow. I need to feel it. Okay, sometimes they have the little nasal cannon in their nose and they don't think it's on. They want to pinch it and hear it, know it's on. Okay, sometimes we need flow, and that's what you're going. When we get into high flow and oxygen systems, you're going to learn total flow of the system and whether or not you're meeting your patient's demand. I have a demand that I have to have, and that's my minute ventilation times 3. That's my demand. You don't have to know that now. But that's my demand, and you must be, as a therapist, be able to meet my demands, okay? And I might not need a lot of oxygen. I might need 21%, but I need some flow. Y'all need to turn the fan on, right? People get short of breath, they cut the fan on, they let the window down, they fan themselves, right? They want more flow, okay? And so that's important to understand that medical gas is there to provide more flow, okay? All right. Because when you put that medical gas and you mix it with oxygen, now you have, it's going to bleed the oxygen down some, but it's giving them more flow, okay? OSHA, Occupational Safety and Health Administration. They're responsible for the safety of it. They're responsible for the safety of you handling those cylinders. Cylinders should always be stored with a chain on it, depending on if it's an H or a G cylinder. That's the bigger ones. They should always have a chain on it. They should be standing up in the corner properly. You got to make sure you're transporting it properly, not just rolling it on the floor or leaving it freestanding without being chained up. Because if that cylinder falls and the stem is broken off, it's going to shoot like a missile. It'll go through 2 or 3 brick walls, right? If it hits you, it'll kill you. It go up in the air, and then what goes up, what? Got to come back down. And they're super heavy, right? So that's another missile coming back down. And they have killed before. That's why they're very, very dangerous. You have to store them properly, okay? And they have a big helmet on them, a top to keep you from, like a bowling pin. You understand a bowling pin? They have a top that takes off and that shows the stem and all of that, right? But if it's not being used, you got to keep that big, heavy steel screw on it, okay? Because if it falls, it protects it, okay? So OSHA is not playing about your storage or your cylinder. They got to get paid. They got to find something to do. So they will come to your department and say, oh, you got too many cylinders in this room. Based on the cubic feet of the room, you can only have a certain cubic footage of cylinders, right? You can't have a closet with 50 tanks in there. Not going to happen. If something happens, it's a problem, okay? You can only have a certain amount in each room. You have a set for empties and you have a set for fulls, right? Empties must be labeled with red and fulls are empty. Fulls are labeled with green, okay? And they have to be in certain areas that will have certain kinds of walls and fireproof doors. All that kind of stuff is important. And OSHA will come around and cite you for this, cite you for that, hit you for this, hit you for that, okay? But that's good, because if you're not following safe processes, you could hurt somebody, right? Not only you could kill your patient, but you could hurt yourself, right? If somebody that's new therapists ain't caring, they don't have no kind of structure or safety or anything, rules or regulations, and one of them tanks fall and explode, it's over, right? It's over. So OSHA protects your safety. Now, these are some other recommending bodies. These are some recommending bodies. You got CGA, which is the Compressed Gas Association. They created all the safety systems that go on cylinders. Remember, we said one safety system was what? Knowing which tank I'm dealing with by just looking at it. Which one of the safety systems is that? By just looking, I know which one that is, because I said in the United States, oxygen is what? Green. So what's that system called? Color coding. Color coding. Medical gas is yellow, right? Nitrogen is black. Carbon dioxide, I think, is gray. I need to be able to see that, right? So that's one safety system. So if an emergency, I'm going to need oxygen, I go right to the green one. I know that's oxygen, unless I'm colorblind. If I'm colorblind, there's some other safety systems that we have, okay? So the CGA has created these safety systems, which you will learn in detail, okay? The NFPA is the National Fire Protection Association. They're for fire prevention, and they govern the storage, right? They govern the storage, but OSHA will come and cite you for it, okay? But the fire protection, they don't come around checking. And sometimes they come check your, you know, the people that come and do the fire hydrants, not hydrants, but the extinguishers, right? That's the Fire Protection Association. Well, you know, maybe subcontract that job to somebody to come out and check those yearly, okay? And they have a little card on there where you have to punch that I checked January, I checked June, I think every 3 months, something like that. They have to come and punch that they checked it and put their initials on there. Because in the fire breakout and you ain't checked and the pressure is down in there, it ain't gonna work, okay? And somebody's gonna die, okay? Because you're responsible for getting all your patients to safety in a fire in the hospital. You're responsible for cutting off the oxygen, because oxygen supports combustion. Oxygen is not flammable. People think oxygen is flammable. It's not, but it does support combustion, okay? Which is a real thin line. If I got a flame and I blow some oxygen on it, I got a flame, okay? It supports the combustion. Combustion is anything that's burning. So in the face of anything burning, oxygen supports it. It gives it life, right? If I'm in a room in a house fire and the doors are shut and the windows are shut, the fire may die out in my room, right? Smoky in there, but the fire may go away. But as soon as somebody firefighter reach and open that door and let that oxygen outside go in that room, guess what? Flash burn. They call that back something. I mean, that was a good movie called Backdraft back in the day. Kirk Douglas. That was a wonderful movie. but y'all might be too young for that one. Backlash. So as soon as you open that door, the oxygen, woof, you can hear it, okay? It sucks it up. It supports the combustion. If I have a candle and I put a cup on top of it, what happens to the flame? It goes away. If I put the top on a candle, it's gonna go out because you suck the oxygen out. That's all the reason. If you open it back up before it's all the way out, it'll come back, right? Depending on how much once you have extinguished it though, there's no more combustion. So oxygen supports combustion as long as it's combusting, okay? All right? But it's not flammable. Then you have the Z79, which is the Committee of American National Standards for anesthetic equipment like ventilators, vent bags, reservoir bags, trach tubes, their connections, humidifiers. Like these is a trach. These are trach tube right here. Remember we said trach tubes. You got the humidifiers. You have the oxygen tanks, the cannulas, all that kind of stuff. It's regulated by the Z79. Okay. They make sure that your ventilatory devices are in check, your reservoir bags and your trach tubes and their connectors, because these have a certain size, right? The trach tubes have a certain millimeter diameter. And so it's just like I said, everybody got their hand in it. It's like everybody getting paid, okay? Making sure you're doing what you're supposed to do. It's for the safety of your patients, but they also getting paid, all right? Somebody got to have a job. Somebody got to do it. And I respect that. Get your money. All right. So that's the Z79. Safety systems. Now, don't ding me for these colors. I just put this picture up for the sake of colors, okay? Some of these look kind of off. But green for oxygen, carbon dioxide is gray, but they got some other things here that are a little bit different. But color coding for E cylinders is the first safety system. The E cylinder is the one that you see Mr. Johnson with at the casino. E cylinder, and I'm gonna show you some cylinders today, or I mean probably tomorrow. The cylinders are, what time is it? Oh, let's say, I think it's 12:10 already. I'll be an hour behind, I forgot. Good. E cylinders are smaller. Now, not too small, but that's the one that's kind of long. You know, you have Mr. Johnson has rolling it on the little cart. Okay, that's your E cylinder. And at the break, I'll go and get a couple and bring them back. And then you have H cylinders and G cylinders, or big cylinders, right? And then you have some smaller than E, like M6s and Ds and stuff like that. You're only going to be testing on the H cylinder and the E cylinder for your lab, okay? You have to be able to construct or operate an E cylinder and a G cylinder, all right? Now, these are the colors. Color coding is only mandatory for the E cylinders. They're not mandatory for the big ones. They are color coded, but they don't have to be. So you need to know what you got, okay? All right, oxygen is green, but it's white internationally. Carbon dioxide is gray. Nitrous oxide is blue. Cyclopropane, orange. Helium is brown. Ethylene is red. Air, regular medical air, is yellow. And nitrogen is black. See, this nitrogen should be black on here, but it's kind of dark gray. These are the color codes of the E cylinders. You got E cylinders in any gas. Just because it's an E tank don't mean it's oxygen, okay? It depends on what it is. If it's an E cylinder, it's going to be color coded for you, so you don't make that mistake. All right? That's the first safety system. So what do you think will be a good safety system for the next safety system? Okay, what if I'm colorblind? What do you think before we go to it? What do you think will be something that would be good to be able to signify the difference between some cylinders? Size, well, that would be a good for distinguishing how much I got, but what about safety? Something to keep me from, when I say safety, I'm saying keep me from inhaling nitrous oxide. I'm thinking I'm getting oxygen, but I accidentally got nitrous oxide because I was colorblind. So what else could you do? Because all the gases are in all the different sizes. So what else could I do that you think would be good to keep me from inhaling the wrong gas? Okay, a lot. What you think? A label, okay, and which can probably come off or something, right? So, Miss Thomas, what you think? Is she still on here? She gone? Okay. All right. What about the next one is called the pin index safety system. Not being able to put the wrong regulator on the wrong tank. That's a good one, right? Each cylinder or each cylinder has pin positions. See this right here? This is pin, oxygen pin position is 2 and 5. The only regulator that's going to fit on this oxygen cylinder is a regulator that has 2 and 5 for oxygen. So I can't, if I have a nitrous oxide E cylinder, but I'm colorblind and I got an oxygen cylinder, an oxygen regulator in my hand, it's not going to fit on that nitrous oxide, right? Because it's the wrong pin position. So the pin index safety system is for E cylinders and smaller. I call them the little pissants, right? P-I-S-S, little pissant tanks, all right? Those are the ones for the E cylinder and smaller, little pissant tanks, little bitty pissants, okay? P-I-S-S, all right? The pin index safety system, the P-I-S-S is what you're going to see it written as, the P-I-S-S. Look at the pin positions. You have a yoke and pins. The yoke is the screw part on the one side of the cylinder, and the pins will enter in the other side, okay, properly. You got 654, then you have 7321. This is all of them, but only the certain cylinder has the one that is 4. So oxygen has pin positions what? 2 and 5. So it's going to be 3 spots on this side and 1 on the other side. You screw it right in there. It's going to be lined up with the 2 and the 5 only. All right. So that's how we know oxygen is 2 and 5. Okay. What about air? Look at E. What is air? What's pin position for air? 1 and 5. What about carbon dioxide? 1 and 6. So a 2 and 5 regulator would not fit on a 1 and 6 cylinder. A 2 and 5 regulator would not fit on an medical air tank because it's 1 and 5. It's not going to do it. Okay. So that's the second safety system. If I'm colorblind, right, I know to use the right regulator, okay? What about the third third safety system, the American Standard Safety System, ASSS, for the big ass tanks, okay? I'm just being real. It's for tanks that are larger than these cylinders. For your big tanks, you use the American Standard Safety System, the big ass tanks. ASSS, right? Ain't that what it says? Okay. So those are the ones that are for the big ass tanks. Okay. The larger than E cylinders use the American Standard Safety System because the larger ones don't have to be color coded. Okay. It's only the color coding is only for the E tanks and smaller, right? But if they're bigger, they don't have to be color coded. They might be, but they don't have to be. And so we use the the ASS for big ass tanks, right? Larger than E cylinders. They are very, very high pressure, and they use the nipple and threaded nut, okay? The nipple and threaded nut. All right, so let me go one quick second. Time we just had a break. So I'm going to pause the recording and grab a couple of regulators right quick, just so you can see as I'm talking, okay? Okay, guys, we have moved over to the lab. And just to give you a better idea of what we're talking about. So a recap, we have safety systems. The first safety system for the E tanks and smaller is the what? The first one before these. First safety system for our cylinders. For the E cylinders and smaller, the first safety system is before that one. When I know when I'm looking at them in Europe, is one thing, in America is color coding. So color coding will be the first, safety system. But if I'm colorblind, I can use the next one, which is the PISS for the little pissant tanks, right? E cylinders and smaller. PISS for the little pissant tanks. They are lined up with pin positions. We said that oxygen is 2 and 5, and air is 1 and 5. Carbon dioxide is 1 and 6. So if I'm colorblind, I'm able to still not make a mistake of hooking to the wrong cylinder because the regulator is not going to fit. Okay. So the oxygen regulator is not going to fit on a medical gas cylinder, and the medical gas cylinder regulator is not going to fit on an oxygen cylinder. Okay, and so that's how we do that. And then after that, we have for the larger cylinders are the ASSS. ASSS, yeah, the big ass tanks, right? For tanks larger than E cylinders, and they are the nipple and threaded nut. So let me show you the difference. All right, so the PISS, guys, is the pin index safety system. You notice it has the pins here, 1, 2, and this one right here fits into the middle of the E cylinder. So oxygen is 2 and 5, right? So this will be 2 and 5 would fit right over your oxygen E cylinder, right? It's the yoke. This is the yoke because I turn it and it will tighten down on the cylinder. See how it tightens down, right? That's the yoke and pin. The PISS uses the yoke and the pin for connecting, right? Then when I get the bigger tanks, the ASSS is the American Standard Safety System regulators for the bigger tanks, right? Big ass tanks. And those will be that's made out of the yoke, not the yoke and pin, but the nipple and threaded nuts. Let me get that. So here's the nipple and threaded nuts. All right, so notice, this is for the bigger tanks, so the American Standard Safety System. It has the nipple and threaded nut. See that? The nipple and threaded nut is the ASSS. The yoke and pin is the PISS. This is for the E cylinder and smaller, and this is for the H tanks, or the bigger tanks, the big ass tanks, right? The nipple and threaded nut. Now, the way it works is, this happens to be an H cylinder, okay? This is an H cylinder that when you store it, it's stored standing up like this. See how big this is? You have your stem here. This is considered the stem. Very dangerous. If this was to fall off and that stem get knocked out, this turns into a missile, okay? Turns into a missile. And so to protect that stem, it has, I call it a little helmet. A little bowling pin looking helmet. Okay, looks like this. This fits over and screws shut. Okay, that way when it's secure, if it falls over, it hits this helmet and it doesn't break the stem. Okay. So when we take this off, we have our 8-cylinder here, has our stem and the valve to cut it on. Okay, very high pressure inside of here. Okay, you're going to learn the steps of cutting it on, and that's called cracking and all of that. But I just want to show you that for the big A tanks, right, the ASSS tanks, you use the American Standard Safety System regulator, which has the nipple and threaded nuts. Okay, that's what it looks like. And so you simply line it up, put over there, and tighten it up. Okay, that's how you turn this on for my larger cylinders. Okay, and now it's on. All right, now what about the E cylinder for the yoke and pin? The yoke and pin cylinders, for the E cylinder, this this is the one you see Mr. Johnson with at the casino. Okay. This one here. This is an E cylinder. Okay. Notice on the E cylinder, it has, one side has how many holes? 3. And the other side is simply a little indentation for that pin to stick in there. Okay. All right. So you have the 3 on this side. Those 3 there will line up with these 3 in here. See that? You see it on your screen? Okay. This is for the PISS. And I will simply just take this over here. I gotta make sure this is open, right? Slide it over there till it catches. Once it catches in place, I tighten up the yoke. Okay, yoke and pin. Turn it on, and I'm ready to go. Okay, that's how you hook up the E cylinders with the yoke and pin regulators. Okay, when I'm ready to take it off, I unscrew it. Right, slide it up off of there. Done deal. So if I'm colorblind, this 2 and 5 won't fit on a yellow one, right? A medical air one, or a nitrogen one, or a carbon dioxide. It's not going to fit. So that helps me with my safety. And I'll put it back in this little storage container so that it doesn't fall. Okay? So those are 2 of the safety systems right there. We learned color coding, and then after we get to the bigger systems, we go into PISS and the ASSS, right? All right, let's see what's next. All right. Oh, and this, for some reason, this didn't get highlighted, guys. So this is the next one, right? I'm gonna have to fix this. But look right here. The diameter index safety system is the 4th one. See how it says number 4 right there? For some reason, it got put in for the PowerPoint, but I'll fix that. But number 4. The 4th safety system is the diameter index safety system. That's known as the DISS. The DISS. And that's just simply all of the connections after the regulator. So if this is the regulator, everything that hooks up to the regulator on the other end of the regulator is regulated by the DISS. So that would be my nasal cannula, my little mask, whatever I hook up to the oxygen cylinder. This part here is considered to be the DISS. Okay? Low pressures, less than 200 PSI, all connections after the regulator, okay? Also the threaded nut and nipple. So most of them will have something like this. See this little threaded nut, right? It will have something like that. You can screw on your mask. You can screw on whatever little device you're using if that's what you want to use, okay? That's the DISS. So we have the color code, PISS, ASSS, and the DISS, right? So let's review. Everything after the regulator is which one? Everything after the regulator. DISS. The one that deals with the pins is called the PISS for the pissant tanks. All of the E cylinders and small. Okay? E cylinder and small. What about the threaded nut and nipple? ASSS, right? That's the ASSS. All right. And then finally, for me to just look, if I'm looking at them, just looking at a bunch of them, color code, right? Color code. All right. Let's look at the qualities of cylinder gases, and then we're going to stop. Okay. Qualities of cylinder gases, and we're going to stop for the day. What are the qualities of cylinder gases? We got to understand cylinder gases have certain qualities. First one is flammable. There are some flammable gases. Some of them are flammable. And that will be ethylene and cyclopropane. Ethylene and cyclopropane are your flammable gases. Then what's next? Non-flammable gases are your nitrogen, carbon dioxide, and your helium. Those are non-flammable, okay? You ever notice when they're blowing up balloons for a party, the helium tank is always what? Brown. because helium is brown, okay? But it's non-flammable. That's one of the qualities, okay? Now, what about the gases that support combustion? Oxygen and anything that has oxygen in it, okay? As well as nitrous oxide. So oxygen, nitrous oxide, and anything that has oxygen in it support combustion. Those are the qualities, either flammable, non-flammable, or supports combustion are the three qualities of cylinder gases. Flammable, non-flammable, or it supports combustion. You learned about the ones that are flammable. You just learned about the ones that are non-flammable, and the ones that support combustion, okay, would be oxygen, nitrous oxide, and anything that has oxygen in it. So when I say oxygen in it, I'm talking about the mixtures. There are some medical mixtures of gases that you're going to be learning about. One is heliox. When they have helium and oxygen mixed, that's heliox. Then we have carbogen, which is oxygen and carbon dioxide mixed together. Then we have oxygen and nitrogen together, or oxygen and nitrous oxide together. Those are all support combustion. Just remember that anything that has oxygen in it will support combustion, okay? Now, what is a quality of helium that's different than everything else that you've noticed over your life? What is helium? It floats, right? It's less dense than oxygen. And so the reason why sometimes we use heliox is because we might have an airway obstruction, okay? So if I have a tumor in my left main stem bronchus and air can't get in there, sometimes we use a heliox mixture that will lift the oxygen up over the obstruction, okay? And that will kind of help that oxygen get down into the parenchyma of the lungs and not get blocked, because oxygen is heavier than helium. So when we put a little helium mixed with it, it will help lift that oxygen up to float over the obstruction, okay? So that would be a reason why we use heliox. The other ones you don't have to memorize because we don't use them a lot, okay? But heliox is a mixture that you will see that we use it in different percentages, okay? So tonight, I want you guys to, tomorrow we're gonna go over cylinders and bulk O2, talk about the quality of just oxygen itself, okay? And getting into the liquid oxygen and all of that. Tonight, there is no homework for tonight. You did your test, that's your attendance for today. If you did not take your test, you need to email me so I can do something for you you can have attendance for the day. Okay, there's gonna have to be something, a little question or something you can answer to give you attendance for today. All right, go back over this PowerPoint. You can go through it, look at the gas law video if you want to at home, and be ready tomorrow for continuing on. Now, you have reading. Let me look at the syllabus right quick so we can make sure everybody's on the same page with the syllabus. When to expect the exam, when to expect the lab. Get rid of this right quick. Go to the syllabus. All right, let's look at the syllabus. All right, so we are, all right, here we go. We just took acid-base chemistry. All right. Oh, there we go. Yeah, we took the acid-base chemistry test. What's today? The 5th. So we took it on the 5th. We should have took it yesterday, but we took it on the 5th. So we started RT210F, which is gas physics, right? The chapters to read for this tonight, guys, you need to be going over Egan's chapter 6 and chapter 40. Don't worry about the seals because we don't have that book in stock yet. I'll check on that today to see if it's here. But focus on Egan's chapter 6 and chapter 40. The homeworks that are on this one are 1, 2, 3, 4, and 5. And of course, don't worry about the workbook. I'm not gonna make you do the workbook. Now, so we first did the first one today, which is Thursday. Friday, we're gonna continue on with the lecture, right? Monday is lab day. You come in on Monday, we're gonna do lab, which is chapter 9 in the lab book, okay? It's gonna be talking about how to assemble an H cylinder, how to assemble an E cylinder. We're gonna learn a lot about that tomorrow, so make sure you're live at least or here on campus, because tomorrow I'm gonna be showing, me demonstrating the proper procedures for the E cylinder, the proper procedure for the H cylinder. Tomorrow you're gonna learn duration of flow, that formula to tell me how long does Mr. Johnson have at the casino before he run out of oxygen, right? You'll have to be able to do one of those as well for your lab. So we're gonna have 2 sessions, 8 a.m. to 12, and then one from 1 to 4 on Monday, okay? When you come in on Monday, make sure you have the lab book page 137, 1 through 5 questions ready for you in your hand. All right, you don't have to turn out your book as long as I see it in your book. That's the red lab book, page 137, numbers 1 through 5. That's what you're gonna have on Monday. You don't have to have it tomorrow, but have it on Monday. You must have it in your hand when you come to lab. All right, now you must feel free to go ahead, guys. I have the lab already recorded in the module. You can look at the lab, watch me put the stuff together, take it apart, put it together, take it apart, the duration of flow, all of those things you have at your fingertips. Go and watch it so that you'll be abreast of all the information. So when it's not free, new information to you when you get here. So tomorrow we're going to continue on with the lecture. And then Monday, you're going to come in and do lab. All right. Now, while I'm doing lab, if there's anything in the lecture I need to finish up, I will. Okay. Because Tuesday is the exam. Okay. Tuesday is the exam for this section. It's just cylinders. It's not that big. It's not that bad. Okay. But this is the cylinder exam will be on Tuesday, the 10th. All right. So Monday the 9th is lab day. You must be here either 8 to 12 or 1 to 4. Tuesday is the exam. And we will then start on gas therapy. All right. And that's actually giving oxygen and what oxygen is doing to the body and all of that. All right. So let's get this one out of the way. It's one of the easier units, but it's some information that you can't just take for granted. So come tomorrow on time, be ready to go through this lecture. We're going to have a strong lecture all the way through the whole day tomorrow, showing you some stuff by hand, letting you work out some duration of flows and all that kind of stuff, right? And then Monday, over the weekend, you need to be studying, reading, so that you can complete these lab book pages on 1 through 5 on page 137, right? And when you do that, you'll come in, hand it to me, and we'll check you off on setting up an E tank and an H cylinder. That's all it is, okay? And you're done, all right? You'll be done for that day. And of course, Tuesday will be the exam, all right? So feel free to email me, let me know, hey, Mr. McCarthy, I want to come in from the 8 to 12 one, or I want to come into the 1 to 4 one, all right? And then that way, that's cool for Monday. And then Tuesday is, of course, 8 a.m. for the exam. So just email me, let me know, because I don't want if every single person tries to come at 8, it might not have much space. And I'm sure everybody not going to want to do the same time. So 8 to 12, 1 to 4. Now, please be advised, if you sign up for 8 to 12, that don't mean you can come at any time between 8 and 12. If you sign up for 8 to 12, be here at 8, because there's going to be some explanation and some kind of instruction involved. You can't let me start and I'm 8, 9 o'clock instructing, and here you come at 9:30 and I have to start all over for you. I can't do that. So if you're going to be here for the 8 to 12 session, be here at 8. All right. And by the time 12 gets here, I would have gotten a little bit more teaching and instructing and then check you off near the end of that section. Okay. If you're going to be here from 1 to 4, be here at 1, not 1:30, not 2:30. Be here on time, because it's going to be the same instruction that I gave the first bunch to you. All right. So be respectful of your peers, be here on time, so we can get this out the way, because I don't want to be teaching this 10 times, all right? I'm only going to do it twice, so be on time. If you get here, if it's 8 to 12, you sign up for 8 to 12, and it's 10 o'clock or 9:30, I'm going to send you away until you come back at 1, because I cannot go back to re-instruct it for you, okay? So make sure you pick the right one. If you want to come at 1 so you can be here at 1, then that's fine, all right? So email me, let me know. But tomorrow is going to be flat foot instruction. So it's going to be very important that you watch the lecture tomorrow, or either be live or watch it recording, okay? Make sure you get that done, because when Monday comes, I don't want to be reteaching any of this. You should be already letting me know. You should let me sit down and show me about setting up these cylinders, all right? All right, have a good day. Be careful out there with this political climate. Watch your surroundings, and I will see you guys tomorrow. All right.